tissue culturing in space using bioreactors. On the ground, the history of doing tissue culturing has been in a petri dish or on a 2D surface. On a two-dimensional surface, you get two-dimensional cell growth. Well, in our bodies, our cells don't grow in 2 dimensions, they grow in 3 dimensions. And we know that the biochemical processes that take place differ in a 2-dimensional versus a 3-dimensional matrix. So the physiological system performs differently under space conditions where tissues grow and freely in a 3-dimensional matrix. And that's what these bioreactors allow us to do. This was developed down at the Johnson Space Center. They began in the 1980s, theorizing that they could improve ground-based research just by going from 2 to 3-dimensional neutral buoyancy conditions. They always had in the back of their mind that the process could be even greater improvements if you could go up to space and do the full 3-dimensional tissue growth in space. And this is what we see an illustration of here. This was also conducted on the Shuttle Mir program, I believe. And what you see at the top are the ground specimens, and the bottom are the space-based systems. It's a 14-day period. And you see a very fine, hazy dispersion of these orange particles. It's pretty uniform. It's all the way across the container. It's like dust. It's a little bit hard to see on this projector here, but you see that in space, those particles begin to agglomerate. And in fact, by the end of day 14, we end up having this was done on prostate cancer tissue. We end up seeing prostate cancer organoids that are an order of magnitude larger when grown in space than they are on the ground. When you can grow this kind of cancer tissue an order of magnitude larger, your ability to interact and have insight into what is the gene expression that's affecting this, what are the regulatory pathways that are allowing this, what are the biochemical reactions that are taking place, it just opens it up the same way the scanning electron microscope opened up our visibility into the molecular structure. We're going to restore the bioreactor cell culturing program on the space station once we get a budget approved to do so. I'm going to give you 3 more of these. Okay, this is probably the most well-known area in macromolecular crystallization. Protein crystal growth has been popularly called. We began doing these experiments in the 1980s through a commercial space center and through a NASA-funded grant program. It was a very robust program. Took place over a 15-year period. There were literally hundreds of macromolecules grown in space under a variety of techniques. What we found was that in many of the cases, you needed 30 to 90 days of exposure time in order to fully grow out the crystals to the large scale that would be needed for X-ray diffraction or neutron diffraction. Well, the program was interrupted and discontinued. 2 years ago, Professor Urati at the Biosciences Institute in Tokyo entered into a relationship to conduct crystal growth experiments in the Russian segment of the space station. I want to get all the facts exactly right here. And Dr. Urati's team was pursuing an enzyme that is causative in Duchenne's muscular dystrophy. They successfully produced the crystal on the right. It's roughly the same size as the crystal that was produced on the ground, but you can see the obvious uniformity in the crystal. Results of over 20 different experiments on 20 different crystals that had a higher resolution, yielded higher resolutions, were presented to NASA 5 or 6 years ago, and those are all a matter of record. This is not an isolated case. What it requires, though, is extended duration on orbit, not just a 5 or 10-day period that we used to be able to achieve on a space shuttle mission. Now, to finish Dr. Urati's story, his research team successfully determined the structure of the enzyme. From that structure, they designed a drug to interdict with the enzyme, and then they administered that drug to 2 canines suffering from muscular dystrophy. And Dr. Uradi presented these results just a month and a half ago at the International Astronautics Congress in Prague, Czechoslovakia, and revealed to the public the progress that had been made in the drug that was designed to relieve, to decelerate the progression of muscular dystrophy, and showed the movies of the dogs before and after the administration of the drug. So there is reason proven that we can use macromolecular crystallography techniques in space to yield the structures of important macromolecules for use in drug design in diseases that plague populations around the world. And it's all a matter of record. We even have testimony from Nobel laureate Bernard Hauptmann back in the mid-1990s to Congress that the space station era would open this field up widely once you could produce a large number of samples and you could do them extended durations on Earth. Gene expression. Genes are the switches that regulate the physiology of our systems, animals, plants, humans. Gene expression is radically different under microgravity environments. These are studies that were done by Hammond and a research team at Tulane University during the 1990s. And it takes a little while to explain them. But what you see on the right, it's a log-log curve. So when there's no difference between the space and the ground samples, you end up along the diagonal in the center, the 0 line. And then as genes either upregulate to the upper left or downregulate to the upper right, they show up spread away from that origin. And obviously, in all systems, there's going to be some degree of abnormal activity, just as background noise. So what the PI did was they said, well, we want to see at least 3 replications of a gene upregulated before we count it as a significant departure from the norm. And you don't see many of those. The 3 line is right around here. This is 3 and 5. So you don't see many of those departures in the rotating wall vessel on the ground, but you look at the spread that you get on orbit, and it's proof positive. In this case, I think there were 1,600 genes that came out significantly expressing different on orbit than they expressed on the ground. This is a fundamental regulator in physiological systems. Okay, and I'm going to finish off on an example that you've heard several times mentioned this morning, but I want to put it in a slightly different context here. You've heard a lot about salmonella bacteria growth and the ability to potentially produce vaccines as a result. It's actually driven by a combination of the differences in gene expression that we talked about and the ability to develop an assay that allows you to determine which of those strains of salmonella end up acting as vaccines on orbit and then being able to bring them back down to the ground and prove that in animal trials. What this is a photomicrograph of an extracellular structure, a biofilm, that's forming around the cells when they're grown in spaceflight environments. Now what that biofilm is doing is it's protecting those pathogenic cells. So it's making it more virulent. So if you can understand what it is that's causing this biofilm to form, then you can understand what's driving up the virulence in the cells. If you can identify which genes are up or down regulating and causing the formation of the biofilm, then you can knock out those genes. So it's the same scanning electron microscope example. You're, through an advance in technology, being able to deploy experiments in space through things like bioreactors, electromagnetic levitators, diffusion apparatus that do macromolecular crystal growth, you're gaining insights into the next lower level at the molecular scale of what is the cause and the effect of disease. To finish this story out, the salmonella vaccine is a good demonstration if it's proven out, but what's far more important is not the vaccine for salmonella. It has a very relatively low market value, although it has huge humanitarian value in the third world where a lot of people, the mortality rate is directly attributable to diarrheal diseases. But what's far more significant is you've got a method, a protocol for identifying vaccines to bacterial pathogens. So now let's move on to a bacterial pathogen that's more threatening, like methicillin-resistant staph, or any of a number of bacterial pathogens. So through assay techniques in space, we have the potential to develop protocols for new vaccines against bacterial pathogens widely distributed on the ground.